Vaibhav Gupta, currently a student of Computer Science and Engineering Department, IIT Bombay. I secured an AIR 54 in JEE 2009 and today we will be learning some basic concepts of electrostatics. That is, we will be learning something about electric charges, fields, and then in the end we will be studying Gauss law. So let's start the chapter of electrostatics by understanding actually what do we mean by electrostatics. Electrostatics is the branch of physics which deals with the effects of a electric charge. So in this definition, every word will be familiar to you except the word charge. So actually, what do we mean by a charge? This word is new to you. So firstly, let me tell you that the properties of charge are somewhat similar to the properties of mass. Firstly, let's talk about the definition. Charge is that property of a substance, you can say, or matter that helps it in affecting its surroundings in an electrical or magnetic way. That is, let's say if here is a point charge. So what do I mean by a point charge? That this has the charge on this mass. Let's say, okay, not talk about a point charge. Let's say this is a matter of mass m. If I say that this body has some charge, let's say plus q. So what do I mean by that this property has charge? That means that this property, this matter can affect its surroundings in an electrical or magnetic way. So this is a physical property of a charge which is similar to the mass, as I told you, as mass is defined as the physical property which affects its surroundings in a gravitational way. So this is the definition of charge. Charges, let's study the unit of charge. Unit of charge. The most commonly used unit of charge is a coulomb. Coulomb is the most commonly used unit of charge, coulomb. But the CGS unit or the SI unit of charge is not coulomb. The SI unit or the CGS unit of charge is actually electrostatic unit, generally denoted by ESU. And 1 coulomb is equals to 3 into 10 to the power 9 ESU. This is the conversion of a coulomb and a ESU, which is electrostatic unit, which is the CGS unit of the quantity charge. Now, the dimension formula of the charge, with in the future you will be able to derive the dimension formula, but for now, note down that dimension formula of the charge is M0, L0, T1 and A1, where this A is the unit of current, that is ampere. So dimension formula of charge is M0, L0, T1 and A1. So this is the dimension formula of the charge. Now let's study some of the properties of charge. Properties of charge. Basically, we have 4 properties of charge. Firstly, that charge is a scalar quantity. As I told you right now, charge is a scalar quantity. That means that there is the charge, the quantity charge does not carry any direction. Only the charge carries only value which may be either positive or which may be negative. Secondly, charges are of 2 types. Charges are of 2 types. One is positive charge and another one is negative charge. So these are the 2 types of charges which exist, and you all know from lower classes, from class 9th and 10th, that same charges repel each other and opposite charges attract each other. So this is a positive charge and negative charge, and let me tell you that actually, let's say this is a matter let's say this is a body. We all know that it has positive charges as the nuclei and electrons floating around it, floating in it actually. So electrons are floating and these positive charges are the nuclei, basically the nuclei of the atom. But we know that nuclei of the atom is a fixed entity, that is, it does not move here and there. So we know that in a matter, electrons are the one which move around here and there. So what do I mean by let's say I say that a body is positively charged. So by positively charged, what do I mean is that I mean to say that some electrons have left the body and thus a body is positively charged. So when electrons leave a body is positively charged, and when an electron enter a neutral body, it is said to be negatively charged. So you'll find that basically a body means charging of a body basically depends on the flow of electrons. One more thing, that as I told you, let's say this is a matter. So if it is, let's say, negatively charged, so we know that it has more of electrons. So if the same body was positively charged, that means it has less of electrons. So we can say that mass of negatively charged body is greater than mass of negatively charged body is greater than mass of positively charged body. So this can be realized as a general concept, that mass of a negatively charged body is greater than mass of the positively charged body, because in negatively charged body number of electrons are more. Third property, charge of an independent system remain conserved. This property says that charges of an independent body remains conserved. Independent system. So what do I mean by independent system is that let's say here is some body, here is another body, and here is the third body. Let's say it is positively charged, it is negatively charged, and it is neutral. So if there is some interaction between these two, there is some interaction between these two, there is some interaction between these two. So they have mutual interaction between each other. So if I consider our system to be this body only, then I can't say that this system is independent, because this system is interacting with its surroundings. So this system is not independent system. So for this body, the charges may not remain conserved. Similarly for this body, and similarly for this body. So independently for these three bodies, charges may not remain conserved. But if I choose my system to be comprising of all the three bodies, I can say that this system is not interacting with its surroundings. That means this system is an independent system. So the system of these three bodies will have, means the charges in the system of these three bodies will always remain conserved. And this property, no, nothing. So this was something about charges being conserved. And the fourth property is charge is quantized. So what do I mean by charge being quantized? Charge being, as I told you, that charging a body is nothing but removal or additions of electron. So charge is quantized. This means that in a body, if you say the charge on this body, the total charge on this body, it can be only an integral number of E minus 1. So where n can be minus from here minus 3, minus 2, minus 1, 0, 1, 2, 3. So n belong to basically integer set. So q is equals to ne. That is, the charge on this body can only be an integral multiple of E, which has a charge 1.6 into 10 to the power minus 19 coulomb. So charge on a body can only be an integral multiple of this quantity. And that is the statement said by the property that charge is a quantized value. So these are the four major properties of charge. Now, after studying that what is a charge, now let's study what are the various methods by which we can charge a neutral body. So first, the most basic method of charging a body is by charging it by friction. Charging by friction. So charging a neutral body by friction. You all know the concept of friction. Friction is the, you can say, interaction between surfaces of two solid bodies. So if you want to, let's say if this is a mass and this is another mass. Now, what happens is if you rub these two masses, sometimes you may have seen that if you rub two rocks, there may be you can say lightning coming out of it. So what is that is when these two bodies are rubbed against each other, there is heat produced between them. So due to that property, some electrons may shift from one body to another. So by means of friction, you may get that if you rub these two bodies, you may get that this body becomes positively charged and this body becomes negatively charged. So this is the method of friction, and you don't need to go into the details of this method because you don't need to find out that what is the procedure of the shifting of electrons in this process. So the point is that charging by friction involves rubbing two bodies and some charges gets transferred, so bodies get charged. Second is charging by conduction. So charging by conduction. In this process, what happens is, let's say this is a neutral body and this is a charged body. So let's say it is positively charged. So this body is positively charged and this body is a neutral body, and they both are connected via, let's say, copper wire through a switch. Now, what happens is this body is positively charged and this body is neutral. So, and we all know that positive charges repel each other. So when you turn this switch on, some of these charges move through the wire and come in this body, and this body gets charged. This body also gets positively charged. So this is the property of charging. This is charging by conduction, and you will, as we proceed in this chapter, you will study that why these charges move from a positively charged body to a neutral body and under what laws these move. One important point that can be noted here is that, let's say, this neutral body and this charged body were both similar in shape, size and mass. And initially this body had +2 coulomb of charge. Then after conduction, both the bodies will have +5 coulomb of charge. That is, charge will be equally divided, but only if both bodies are similar in shape, size and mass. So this is basically charging by conduction. Now let's move on to charging by induction. Charging by induction. Induction, as you know, is derived from the word induce. So induce means ignite something in charges. So let's say if okay, we need one body only here. Let's say this was a neutral body. Let's say this is our neutral body, and we bring a charged rod, let's say positively charged rod, near to this neutral body. So as I told you that we know that opposite charges repel each other, and opposite charges attract each other and similar charges repel each other. So in this case, we all know that a body may be neutral, but it always has charges. That is, it always has positive and negative charges of equal amount, and thus the body in total is neutral. So we may have such types of charges in the neutral body where the amount of positive charge is equals to negative charge, and thus the whole body is neutral. Now, when a positively charged conductor is brought near to this matter, what will happen is, we know that this positive charge will attract the negative charges out of it, means negative charges towards it, and this positive charge will repel the positive charges against it. So what will happen is, these positive and negative charges inside this body will align themselves something like this. All the negative charge will come to this end because it is attracted by this positive charge, and all the positive charge will go to the far end because it is repelled by those positive charge. So this may be the situation of this conductor. But point to be noted is that it is not possible that all of the charge of this body moves, means all of the negative charge moves here and all of the positive charge moves here. It is just some of the positive charges move here and some of the negative charges move there. So this this is actually the property, you can say induction, because this rod without touching has induced some electric forces in this charge, in this conductor. So now what we do is, if I let's say if I connect this body with a copper wire to another body, what will happen with some of its positive charges will move to this body because they all are repelled by it. So some of the positive charges may go to that body. And now if I close the connection, I'll find out that the amount of negative charge here is greater than the amount of positive charge here. So finally you can say that this body will be left out as negatively charged body, and this body will be left out as positively charged body. So this is basically the method of charging a body by induction. Now what means, this was one way of charging a body by induction. The another way could have been not connecting another body but connecting this wire to the earth. So note down that this is the symbol of earth in electrostatics and electric field. We'll be studying more of electric field and whatever. So this is the symbol of earth. So if I connect this body with a copper wire to earth, what will happen is that electrons from the earth will move upwards through the wire and neutralize this some of the positive charge. So electrons move upward and neutralize this positive charge. So once again you will get and if then you close this connection, once again the body will be left as negatively charged body. Now before explaining any further ways of charging a body, let's study something, some properties of matter. The matter that exists in the nature is of three types basically: A, conductor; B, insulator; and C, semiconductor. So these are the three types of material that exist in this universe. Conductor, as you know, as you may know, conductor is a matter in which electrons are loosely bound and are free to move in the whole matter. So conductor is the matter through which electricity can be conducted because the flow of electron is pretty smooth in a conductor. As we know, examples of conductor like copper, silver, etc. So these are the examples of conductor. In insulator, while electrons are tightly bound to the nuclei and only a few are available for the movement in the matter. So insulators are a bad conductor of electricity because since the flow of electrons is not smooth and is hindered by the forces applied by the nucleus, So the electrons cannot flow properly in insulator, and thus electricity is not conducted by insulator. Examples of insulator are wood, plastic, etc. Whereas in semiconductor, the number of electrons which are free is between conductor and insulator. So semiconductor is a whole different branch of physics which deals with these semiconductors, example silicon. So and it is pretty interesting branch also, but it is not much in at our level, so we'll be skipping semiconductors in this chapter. But yes, you will study some of the semiconductor properties in the whole new chapter, that is semiconductors. So these are the three matters that exist in the nature. Now let's move on to the next property, next way of charging, thermionic emission, or means they are pretty little, so let me not write down. Next way of charging a body is by thermionic emission. In this process, what we do is we heat up a matter. So when we heat up a matter, what happens is that electrons gain a large amount of kinetic energy, and thus some of them leave, means some of them comes up, means some of them breaks the force of the nuclei by gaining a lot of kinetic energy, and thus moves out of the matter, and thus matter is left out as positively charged. Next method of charging a body is by photoelectric effect, which you will study in modern physics. Basically, in photoelectric effect, what we do is we take up a metal and we throw a certain frequency of light on it, So what happens is, again the light provides enough kinetic energy to the electrons so that they can escape, means they can come out of the metal, they can break all the bonds with the metal, break all the forces which are holding them to the metal, and thus come out of the metal. So thus metal is again left as positively charged. And one more method is by charging a body by electric field. So we'll be studying that in the electric field topic only, so let's skip it for now. So that was about something about charging different kinds of bodies. Now one point to be noted is that we know that two bodies, let's say you are given that two bodies, you don't know, okay, it is said that these bodies may be charged or these bodies may not be charged. So, but a property is given that these bodies attract each other. Let's say the A body and B body. So it is said that A and B attract each other. And we are not considering gravitational forces, we are just considering electrical forces attract each other. So what all things can you infer from this statement that A and B attract each other? Since we are considering only electric forces, that means there must be one of the bodies must be charged, that is for sure. Otherwise they can't attract each other if we are considering only electric forces. So let us assume that A body is charged, and let us assume it is positively charged, because it does not matter considering that A is positively charged or negatively charged. So without loss of generality, we can assume that A is positively charged. Now what about B? B can be positively charged, or B cannot be positively charged, that is for sure, because if B is positively charged, then A and B cannot attract each other. So the choices left for B are that B can be neutral or B can be negatively charged. In both the cases, both bodies will attract each other, because if B is neutral, then A will induce negatively charged, like A will induce an orientation of charges like this, and if let's say this is A which is positively charged, and this is a body where here are negative charges and there are positive charges. So we know that since negative charges are closer to this positive charge than the positive charge, so we will find out that the force of attraction between these two bodies will be greater, because the opposite charges are closer to each other. So since force of attraction between these two bodies will be greater, so finally if B is neutral, then also A and B will attract each other. Now, okay, so from this statement we can only infer that A and B, one of the bodies has to be charged, and the other may be charged or may not be charged. But let's say if the statement is given that A and B repel each other. Now, if the statement is given as A and B repel each other, then what all things can happen? At least one of the bodies has to be charged. So let's say A is charged. So let's say A is positively charged. Since A and B repel each other, B cannot be negatively charged and B can also not be neutral. So B has to be positively charged. So if it is given that two bodies repel each other, then both the bodies have to be electrically charged and have to carry the same sign of the charge. So we can say that repulsion is a sure test of electrification. So this is something about charges, electric charges. Now let's study as I told you that, as we all know that opposite charges attract each other and similar charges repel each other. Let's study what is the amount of force with which they repel and what is the amount of force with which they attract each other. So this was derived by Coulomb and is known as Coulomb's law since then. Coulomb found out through his experiments that what you can say, sorry, I think spelling is wrong. Coulomb, through his experiments, found out that the forces between two electric charges, that is, let's say this is a charge, sorry, I forgot to mention that forces between two point charges. Let's say this point charge is Q1 and this point charge is Q2. Mind it, I am talking just about point charges which are kept in a same medium. Currently, for the sake of simplicity, which are kept in vacuum, the force between them is directly proportional to the product of the two charges, the product of the charges that the two matter carry. And let's say if this distances r, and the force is inversely proportional to the square of the distance between them. So he found out that force is proportional to the product of the charges and inversely proportional to the distance square between these two charges. So if I consider this, if I take these two things in account, I'll get that force is proportional to Q1 Q2 upon r square. Now if I put a constant of proportionality, I'll get F is equals to K Q1 Q2 upon r square. So this is the formula for the forces which act between two charges Q1 and Q2 in a vacuum. So what is this K? The constant of proportionality. The K, that is the constant of proportionality, is defined as 1 upon 4 pi epsilon naught. In a vacuum, this is K, the constant of proportionality, is basically 1 upon 4 pi epsilon naught, where epsilon naught is absolute permittivity of vacuum. Epsilon naught being absolute permittivity of the vacuum, 1 by 4 pi epsilon naught is this constant of proportionality K. Thus, F formula for the force between these two charges can be written as 1 by 4 pi epsilon naught Q1 Q2 by r square. And similarly, let me remove this proportionality thing. Similarly, if these charges, let's say, were not kept in vacuum, that is, they were kept in some, you can say, a medium. Let's say they were kept in a medium. So F would become 1 by 4 pi epsilon Q1 Q2 by r square, where epsilon is known as the absolute permittivity of the medium. So this is the formula for the force between two charges which are kept in a medium, where epsilon is the absolute permittivity of the medium. Epsilon can be written as, this epsilon can be written as epsilon naught into epsilon r, where this epsilon r is relative permittivity of the medium. So this epsilon, that is the absolute permittivity, can be written as an epsilon r into epsilon naught, that is in a factor of epsilon naught, where epsilon r, which is the ratio of epsilon and epsilon naught, can be written as relative permittivity of the medium. So this is basically the formula for the forces acting between two charges. The value of K, let's see the value of K. The value of K comes out to be 9 into 10 to the power 9 Newton meter square per coulomb square, and the value of epsilon naught, which was 1 by 4 pi K, comes out to be 8.855 into 10 to the power minus 12 coulomb square per Newton meter square. So these are the two standard values. This is the standard value of K, and this is the standard value of epsilon naught, which I think you must all remember, because this is these values are used in various calculations of forces in between electric charges. Now, as we all know that force is a vector quantity, we have studied that the magnitude of the force is this. So what is the direction of this force? The direction of this electrostatic force put by this one charge on another is, let's say this is another charge. So force on Q2 by this Q1 is along the line joining Q1 and Q2. That is, Q1 puts a force of K Q1 Q2 upon R square on Q2 in this direction, which may be, yeah, if this is positive though, so that means they repel each other, that means they are of same charge, and if they are of opposite charge, then they attract each other, and thus the direction would be like this. Pause. So now we know that what is the direction of this force. We know that the force acts along the line joining Q1 and Q2. So let's say if I talk about force between these two quantities, I can say that force can be written as K Q1 Q2 by mod R vector cube into R vector. So in this way, you can see that if I write the R vector of Q2 with respect to Q1, then this will give the force on Q2, and it would give in the direction of the line joining Q1 and Q2. This force can also be written as K Q1 Q2 R cap upon R square. So this is the formula for the force in its vector form. So this is basically what Coulomb's law says. So let's solve a question based on this property of, or you can say based on this formula of Coulomb's law. So the question says that, let's say here is a charge of plus 100 coulomb, microcoulomb actually, and here is a charge of plus 200 microcoulomb, and this is at a coordinate 4, 4, 2, and this is at a coordinate 1, 0, 2. So you have to tell the force exerted by plus 100 microcoulomb charge on this plus 200 microcoulomb charge. So for calculating that force, we can write down that F is equals to K, which is 9 into 10 to the power 9, into Q1, which is plus 100 coulomb, microcoulomb. So it can be written as 100 into 10 to the power minus 6 coulomb into 200 into 10 to the power minus 6 coulomb. So this is K Q1 Q2. Now what we have to write is we have to write the R vector. So R vector can be written as 4 minus 1, that is 3 cap, 4 minus 0, that is 3 cap, 4 cap, and 2 minus 2, that is 0 cap. So 3 cap plus 4 cap divided by the modulus of 3 cap plus 4 cap, which would be root over 3 square plus 4 square, and its modulus is whole cube. So this is the formula for the force exerted by plus 100 coulomb charge on plus 100 microcoulomb charge on plus 200 microcoulomb charge. So this force can be written as 10, 11, 12. So this whole thing gets cancelled out and we are left with 180 into 3 cap plus 4 cap whole divided by 5 5s are 25 into 5, that is 125 actually, but okay. Okay, so calculations you can do next. So this is actually the force exerted, means I solved this question to tell you how do we write the R vector and how do we write the modulus of that R vector. So if you want to calculate the force of on 200 coulomb, you write the R vector of this point with respect to this point, and if you wanted to calculate the force on this vector, you would have written in place of 3 cap plus 4 cap, you would have written 1 minus 4, that is minus 3 cap, 0 minus 4, that is minus 4 cap, and 0 cap. So this is the way we write the R vector in the formula for force in Coulomb's law. So this was something about Coulomb's law. Now let's study principle of superposition. Okay, it's not much to write about it. So principle of superposition. Principle of superposition you may have studied in the chapter force, that if, let's say if this is a Q charge and many electric forces are applied on this Q charge, maybe due to many charges, like say Q1 here and Q2 here and Q3 here. So these all apply different forces on this. Let's say Q1 applies F1 here, Q2 applies F2 here, and Q3 applies F3 here. So what is the total amount of force exerted on electrical force that is exerted on this charge Q due to all these three charges? So the principle of superposition says that the total force exerted by all these three charges can be taken as the vector sum of all the forces applied by individual charges. So this is the formula, or principle of superposition is not basically a formula, it is a concept that the total amount of force that is exerted on an electric charge is the vector sum of all the forces which are independently exerted by these three charges. So this is the principle of superposition. Now let's solve a question based on principle of superposition. This question says that let us design a question. So yeah, we can say that this is a circular path. This is a circular path. So three charges are there of charge plus Q, let's say. Here is charge plus Q and they all are point charges. Here again is plus Q charge and here again is plus Q charge. These charges are placed symmetrically in this circle. Circle's radius is R. So these charges are placed symmetrically in this circle. So if these charges are placed symmetrically in this circle, you can say by symmetry that these three charges form an equilateral triangle. And these three charges are not static, they are actually moving. They are moving in this circle with velocity v. And here is a in the center, charge with minus 2q value is placed. So what you have to find out is, you have to find out the value of this velocity, that is the amount of speed that is with which all these three charges are moving. So, and here is a minus 2q charge. So how do we do this question? Basically, the funda behind this question is that since these let us consider this charge which is rotating with a velocity v around in this circle. We know that forces on this charge, electrostatic forces on this charge, are applied by this plus q, by this minus 2q, and by this plus q. So all these three charges simultaneously apply force on this plus q charge. So what is the total amount of force that is applied on this plus q charge? We can easily find it out by extending this line here, and if I join this minus 2q, so I know that this plus q will repel this plus q, so let's say F here, and since I know that this is an equilateral triangle, so the amount of force that this plus q exerts on this plus q charge will be equal to amount of force that this plus q exerts on this plus q charge. So if this is F, this will also be F. So we have a force here F, we have a force here F, and these are the two repulsive forces, and there is an attractive force applied by the charge minus 2q. So here is an attractive force, you can consider it as F1. So if I want to find out the total force on this plus q, I can write it down as, we know that this angle is 30 because of symmetry. So this angle is 30. So I can say that the total force on this plus q can be written as F1 minus 2F cos 30. So this is the total amount of force, means force towards the center. And since it is moving in a circle with velocity v, this will be equal to the centripetal force, which would be mv square by r. Yeah, this would be mv square by r. So let's write F1 in its magnitude. So F1 can be written as kq into 2q upon r square, because the radius of this circle is r, and minus 2f, f can be written as kq upon the distance between them, and the distance can be written as, since this is r, I know that this is 60 degree, or you can say this is 60 degree, so this is r cos 30, so this would be 2r cos 30, which would be equal to 2r root 3 by 2, which would be equal to root 3r. So the side is equals to root 3r, so in the denominator here would be root 3r whole square into cos 30, which would be root 3 by 2. Yes, and which is equals to mv square by r. So this can be written as 2kq square by r square minus this 2 gets cancelled out. This can be written as 3r square. So it would come out to be kqq by root 3r square equals to mv square by r. So this r gets cancelled out with one of the r's, and this is q square basically. So v square can be written as kq square by mr into 2 minus 1 by root 3. So this formula gives the velocity, this is the velocity with which all the three charges moves in this circle. So you can see the question was pretty easy if we looked upon at every force exerted on this charge by every other charge and use the principle of superposition. So you can see that principle of superposition is a very important tool. As you know, means the amount of force exerted by this charge on this charge is not affected by the presence of any of these two charges. So you will find out that principle of superposition indeed is a very strong principle in itself in future physics also. So this was one of the questions based upon principle of superposition. Now next we'll study something about equilibrium, electrostatic equilibrium. Electrostatic equilibrium. Now, basically, in this electrostatic equilibrium, what happens is, let's say you have, let's take an example which will give you a better idea, or let's study what is equilibrium. You all have studied equilibrium in the chapter Simple Harmonic Motion. That is, if on a matter, the total amount of force that exists, that is exerted on that mass is equals to 0, and if that mass is displaced from its position by a little bit, it either comes towards it, or it either goes away from it, or it either remains at its position. Let's take an example of all this so you'll get a better idea. Let's say this equilibrium basically defined as the state in which the total amount of force on any matter is 0. So, and equilibrium can be classified into 3 types: stable, unstable, and neutral. The most basic example of this can be, let's say if you have some figure like this, means this is a bowl, or you can say anything. So if a ball is kept here, you can imagine that everything is at rest. So the total amount of force exerted means on this small mass, or you can say small bead or whatever, is equals to 0. So this is a state of equilibrium for the small bead, and this whole thing is static, means this can't be moved. So now, since the force here is equals to 0, that means this is a position of equilibrium. Now what happens is, let's say I move this bead a little bit here. So what will happen is, by the action of gravity, this bead will get attracted towards this position again. So if I, let's say I move this bead here, what will happen is gravity will pull again it down towards the point of equilibrium. So when I move this body means when I move this body away from the equilibrium position, it tried to regain its equilibrium position. So this type of equilibrium is known as the stable equilibrium. Now the example of unstable equilibrium. Unstable equilibrium can be taken as, let's say similarly, this was a surface and it is static, and the bead rested on the top of this position. So you can imagine that since it is at the top, the total amount of force exerted by gravity on this, not exactly by gravity, but the total amount of forces acting on this bead is equals to 0. So yes, this is a position of equilibrium. But if I displace it a little bit here, this is the equilibrium position. If I displace this a little bit here, will it try to regain this peak position? No. If I displace it here, what will happen is gravity will pull it down and it will move away from its equilibrium position. So this is an example of unstable equilibrium, where if a body is moved away from its equilibrium position, instead of regaining its equilibrium position, it moves away from it. So that is known as the unstable equilibrium. Now a neutral equilibrium. Let's say let's take an example. Let's say this is a plane surface and I place this bead here. So you can imagine that the total force acting on this bead would be 0. So this is a position of equilibrium. Now let's say I move this body a little bit here. So if I move the body little bit here, will this bead move in left or right, anywhere? No. You can clearly see that this bead will remain again at its position, and again this new position would be a position of equilibrium. So if I move it here or here or here or anywhere on this surface, the total force acting on this bead would be 0. And this is an example of neutral equilibrium, where the body neither tries to regain the position of equilibrium, neither tries to oppose it. So that position is known as the neutral equilibrium position. Now let's solve a question based upon this property of equilibrium. Okay. I'll basically be solving two questions based on the property of equilibrium. First one is, let's say this is a positive charge and this is a positive charge. So we have a plus q here, we have a plus q here, and here in the middle is kept another, you can say, plus q charge if I want. Now this distance is, let's say, r, this distance is, let's say, r. So if I closely see, this electric charge, means this body will exert a force of F in this direction, and this body will exert a force of F in this direction. So you can see that since this body is at the middle of this line joining, let's say, A and B, so the amount of force is the value of force acting on the middle charge is equal but opposite in direction. So the total force acting on this plus q charge is equals to 0. That means this position is a position of equilibrium. Now let's say I move this plus q charge a little bit in this side. So if I move this plus q charge a little bit on that side, let's say by a distance x. So this distance between these two quantities will be r minus x, and this distance would be r plus x. So if the new position is something like this, somewhere here is a r plus q charge, where this is r minus x, this is r plus x. So you can see that now the forces by these two charges are not equal because the distances are no more equal. So this will exert a force, let's say, F1, and this will exert a force, let's say, F2. So you can clearly see that F2 would be greater than F1 because the distances between charge B and the middle charge is r minus x. That is, the distance between these two charges is less than distance between these two charges. So you can clearly see that F2 is greater than F1. That means the force on the left hand side, means the net amount of force on this plus q charge would be on the left hand side. So if I move this plus q charge by a position x here, what will happen is this charge will start moving towards its equilibrium position. That means this position of charge is basically a position of stable equilibrium. We'll calculate its time period, means I'll explain you that this is a SHM and we'll calculate its time period. But before that, let us displace this charge in some other direction. In this part, I displaced it in the line along joining the line which joined charges A and B. Now let's displace it perpendicular to that line. If I displace this charge like this, that is by a distance x in the upwards direction, what will the new system be? New system would be something like this. Here would be charge A, here would be charge B, and somewhere here would be this plus q charge. And by symmetry, you can say that the distance between A and plus q charge and the distance between B and plus q charge will be same. So the forces put upon by A and B on this plus q charge would be equal in amount but different in direction. So this is force F, this is force F on this plus q charge. So if I find the resultant of these two forces, since it is the figure is totally symmetric, the net amount of force that will come on this charge would be here, and if I say this is a theta, so net force would be 2F cos theta in the upwards direction. So now you can see that if I move this plus q charge a little bit in the upwards direction, the total force will take this charge in the upwards direction only. That is, this charge will start moving in the upwards direction. And similarly, if I take this somewhere below, this charge will start moving in the below direction. That means this position is an unstable equilibrium with respect to y-axis. So if I complete the statement would be that this position is stable, is a position of stable equilibrium along x-axis. If I consider this system as x and y. So this position is the position of stable equilibrium along x-axis, but is a position of unstable equilibrium along y-axis. Now, as I promised that I'll solve the part of SHM for the motion along x-axis, let's calculate the time period of the motion of a charge along this x-axis. So we know that this is a plus q charge. This is again plus q charge. And in center we have another plus q charge. Let's say this distance was L. Now, Now the question is, we have to calculate the time period for the motion of this plus q charge. First, let me show that the motion of this plus q charge along x-axis is a SHM. So let us see that the motion of the charge in the middle is actually a SHM. Let's say its mass is m. So for checking that the motion of this plus q charge along the x-axis would be a SHM, let's shift this by a distance, let's say x on this side. So if I shift this by a distance x, the new distances here would be L plus x and L minus x. So the new force that would be applied, that would be acting on this charge towards the, because this would be the new position. Let me draw the new position by blue. So this would be the new position and the total force acting in this direction. So the total force acting would be KQQ by L minus x whole square minus KQQ by L plus x whole square. So this can be written as KQ square L plus x whole square minus L minus x whole square, which would be 4LX upon L square minus x square whole square. So this would be the total formula, that is F would be equals to KQ square 4KQ square Lx upon L square minus x square whole square. But you all know that the force acting towards the equilibrium position in the case of SHM is actually equals to Kx, that is minus Kx, or if I consider the magnitude, it would be F equals to Kx. That is, it is directly proportional to the distance of the body from its equilibrium position. But it is not the case here. So what do? What we do is, we take this x to be much smaller than that value L. We know that we displace this plus q charge only a little bit from its equilibrium position. So if x is much less than r, L square minus x square can just be written as L square. So if I write this quantity as L square, this would come out to be 4kq square upon L cube into x. So this is equals to kx, where this whole quantity is actually equals to the k of the SHM. So I can write down the time period of this SHM as 2 pi root over m upon k, which is equals to 2 pi root over m divided by 4kq square by L cube. 4kq square by L cube. So this is the formula for the time period of the SHM shown by this plus q charge along the x-axis. So this is the basic funda of equilibrium, electrostatic equilibrium. Now let's move on to the second part, that is the electric field. Electric field. So what do we mean by electric field? Electric field can be defined as, let's say this is a whole space 2D, or if I consider a 3D space. So electric field is defined as the total force that would act on a unit charge. That is, if let's say we are considering this 3D space, here is a charge with value, here is a charge with value +1, that is a unit positive charge. So here is a charge of +1 coulomb. So what value of force will act on this charge, that is this unit charge, the amount of force that act on this unit charge by anything in this universe. Means I'm talking about electrostatic forces. So any electrostatic force that acts on this the unit positive charge from the whole universe is defined as the electric field at this point. So mathematically, electric field can be defined as the force acting on a Q0 charge at a point. So as you can see, the direction that electric field is a vector quantity and its direction is given by the total amount of force acting on the Q0 charge at that point. At the point which we are talking about, means at the point where we are calculating the electric field. So this is basically the mathematical definition of the electric field. Now let's one more thing, that okay, you know that electric field is a vector quantity. Another thing is that electric field follows the principle of superposition, same as the force does in the Coulomb's law. That is, we know that in case of force at any point, that is at any charge, if F1, F2 and F3 were the three forces, so the total sum of these three forces was written as F1 plus F2, that is the vector sum of all the three forces. Similarly, at any point, if let's say electric field by one quantity is here, another charge is here and another quantity is here, so net electric field at any point can be written as the vector sum of E1 plus E2 plus E3. So this is the principle of superposition, which is valid for electric field also. Next we have is, this was the concept of electric field. Now let's apply it in some questions and calculate the values of electric field for different shapes, which for different common shapes which are generally asked. Let's start with a point charge. Let's say this is a point charge plus Q. If I want to find out the electric field, now since this is a point charge in the whole space, so if I want to calculate the electric field at a distance r, let's say at a distance r from this plus Q, what will I do is, I'll say okay, here is, I want to calculate electric field at this point. So let us put a Q0 charge here and let us calculate the force acting on this Q0 charge. So force in magnitude would be K Q Q0 by R square. So and the direction would be in this, means along the line. So this is the formula for force. So formula for electric field can be written as F upon Q0, which can be written as K Q divided by R square. So formula for the electric field exerted by a plus Q, a Q charge, a Q point charge at a distance r is equals to KQ upon R square, and it is in the direction radially outward. So if I consider, you can say, if I consider a circle of radius r around this plus Q charge, at every point on this circumference, or if I consider a sphere of radius r around this plus Q charge, at every point on that circle or sphere, the magnitude of electric field will be equal and it would be radially outward. So this is the electric field exerted by a plus Q point charge. Now let us complicate things. This was just a plus Q charge, that is, this was just a point charge. Let's take a difficult shape to calculate the electric field. Let us take a ring. So this is a ring which carries a plus Q charge. So this is the ring. Firstly, let's look at the easy part of this. Firstly, let's look at the conditions put upon on the ring. The ring has plus q charge and it is uniformly distributed on the ring. That is every, means if I, let's say, what do I mean by uniformly? Let's say I take a 30-degree angle here, mean 30-degree arc here, or 30-degree arc here, or 30-degree arc here. All these three parts will have equal amount of charge. So that means that is the meaning of uniform distribution of a charge plus q on this ring. That is, if I take any arc of any angle, wherever I take that arc, the amount of charge in that arc would be equal. So now let's calculate the electric field exerted by a ring. So this is a ring of plus q charge. Let's firstly calculate the electric field by this ring on the center of the ring. As you can see, means maybe some of you got it by intuition or whatever, but you can see that if I consider the center of this ring, I can clearly say that if, let's say, here is a small part of the ring, this is the center, and what I do is I take a small angle d theta and make up an element which contains a charge dq, and the angle between is d theta. So this is the small part of the ring which contains a dq charge. Now this dq charge can be considered as a point charge. So this dq charge being considered as a point charge will exert an electric field at this point in this direction. And similarly, but if I consider the diametrically opposite similar dq charge here, let's say I consider the diametrically opposite dq charge here dq charge, since it is uniformly distributed, the charge here is dq, so the charge here will be dq because the angle is same as d theta. So this dq charge here will exert an equal amount of electric field on this side. So hence, for every dq charge anywhere on this ring, I can find the counter of that dq charge, that is the another part on this ring which will exert equal and opposite force at this point, or equal and opposite electric field at this point. So you can see that the electric field at the center of this ring is 0. So yes, that is true that electric field on the center of the ring is 0. But let us calculate the electric field of the ring at some other point. Let's say this is the axis of the ring, and this is our ring. So I don't think that this is the axis anymore. Axis of the ring would be something like this. So this is the axis of the ring and this is our ring. Now let us calculate the electric field of this ring at a distance of, firstly let us understand how this ring is placed. This ring is something like this, means it is outside the plane of the board. So this ring is something like this, and this axis is like, if this is the ring, so this axis is like this, and what I am showing on the paper is, on the board is something like this. So this is my forefinger and my thumb form a ring, and this is the axis which lies between which passes through the center of the ring. So this is the figure shown here. Now we want to calculate the electric field at a distance of x from the center on the axis. So you want to calculate the electric field at this point. Now, to calculate the electric field at the point, at the distance x on the axis of the ring, what we do is we take up a small element on this ring and we join it by this quantity, or I can say, yes. So what we do is, let's look at the figure on here also. So this is the front side of this ring, that is we are looking from here. So this is the center. Now, what element I am considering is, I am considering an angle theta and then a d theta small element, and here is a charge dq. So here is a charge dq, and what I am considering is an element theta and then a very small element d theta. So this is that small element d theta, and the force exerted, that is the electric field exerted by this d theta at this point, would lie in this direction. It would be, if this angle is, let's say, phi, so, and this radius is r, this distance would be r square plus x square over root. So this force this electric field can be written as k dq upon r square plus x square. Since this is the root, so it can be written as root over r square plus x square whole square, which is r square plus x square. So this is the value of electric field exerted by this dq charge in this direction. Now, see carefully, as the theta varies in this figure, that is, if let's say, if theta varies and the element which we are considering comes here. So the element which, or let's say it moves diametrically opposite. Here is dq. So here somewhere will be another dq, and it will again put up a force on, put up an electric field here, that is k dq upon r square plus x square whole 3 by 2. So the point what I am saying is that when I consider every such dq element, that is I vary theta from 0 to 2 pi in this ring, you can see that in this ring the element will vary like this. So you can say that all this, if I draw such lines for every such dq point, there would be a cone would be formed there, and similarly a cone of the electric fields would be formed there, that is these directions of the electric fields would be followed here. So by the similarity, I can say that every such force, the component opposite will get, the component in this direction will get cancelled out, and the component in this direction would add up, and this added up would be integration of k dq upon r square, sorry, this is r square plus x square, r square plus x square, since this is angle phi, this is also angle phi, so k dq plus x square cos phi d phi. Yeah. So this is the integration of all the, what you can say, this is the integration for, sorry, this is not d phi. We can say that this is the formula, that is k dq cos phi upon r square plus x square is the component of one of the fields on this direction. So the total field would be k dq cos phi upon r square plus x square into the integration with respect to theta. So this whole, the integration of this whole quantity where theta varies from 0 to pi. So for that we have to write dq in terms of d theta. We know that q charge is uniformly distributed in this ring. So I can write this dq charge to be, since I can say that q charge is uniformly distributed in the distance 2 pi r. So I can say in 1 unit distance it would be q upon 2 pi r, and this distance is r d theta. We know that the distance with the smallest, this arc, the length of this arc is r d theta. So in the distance r d theta, the total charge would be q upon 2 pi r r d theta. So r gets cancelled out. So we are left with q d theta upon 2 pi. In the space, that is dq is equals to q d theta upon 2 pi. So let us substitute the values here. dq can be written as q d theta upon 2 pi, and cos phi, as you can see, can be written as x upon root over r square plus x square cos phi. So if I substitute these values here, it would come out to be k q x upon r square plus x square whole to the power 3 by 2, and this would be divided by 2 pi and into d theta, where theta is integrated from 0 to 2 pi. Now we know that x value is independent of, means every term in this bracket, in this integration, is independent of theta, so it can be taken out, and this formula can be written as so this formula can be written as k q x upon 2 pi r square plus x square whole to the power 3 by 2 into d theta integral from 0 to 2 pi would come out to be 2 pi. So 2 pi gets cancelled out. So thus the electric field formula finally comes out to be k q x upon r square plus x square whole to the power 3 by 2. So no, there is no dimensional mistake in this, because this has a dimension of q and upper we have a dimension of one single in length. So okay, this formula is proper, that is kqx upon r square plus x square whole to the power 3 by 2. This is the formula for the electric field exerted by a ring on a distance x along its axis. So I'll recommend that you remember this formula, because the proving this formula can be very hectic, and the point here to be noted is that one more thing that you can derive, that if x equals to 0, that is if we choose the center of the ring, then this formula is giving us the answer 0, which we already proved that electric field at the center of a ring is 0. Now, next point is, let us say x was very less than, means x was very less than r. So let us remove the whole proof of this formula. Let us say x was very less than r, that is x is, so E would come out to be kq x upon r cube. So you can see that if x is very less than r, that is if x is nearly here, we know that this, since at the center the kq upon r cube x, okay, but this force is acting in the opposite direction. Okay, now the point is that if let's say here was this point in the center of the ring, we know that this is the point where the force is 0, because electric field is 0, so force acting on a unit charge placed at the center of the ring would be 0. But what about a unit charge which is placed at a very small distance, that is at a distance x which is much less than r? We can see that the electric field comes out to be kq r cube by x. So the force we all know is equals to q into E. So if force is equals to q into E, we can say that if the q charge, that is, let's say if this total q was positive and the small q is negative, then there would be attractive force, and we'll get that minus k q by r cube into x. F is equals to. So we can say that this is a SHM. That is, if it in a ring, a minus q charge is placed near the center of the ring, then it will perform a SHM around, means about the stable equilibrium position, that is the center of the ring. So this is something about state. One more point to be noted here, that if let's say x was not less than, very less than r, x was much greater than r, then what will happen is electric field will come out to be kq x upon r's can be ignored, it will be x cube. So x and x get cancelled out, it will be kq upon x square. So we can see that E equals to kq upon x square is a similar formula for E, which is E equals to kq upon r square, that was for a point charge. That is a point electric field at a distance x, let's say from a point charge would be kq upon x square. In this case, if x was much greater than r, then the electric field also comes out to be kq upon x square. The point here is that this whole ring behaves as a point charge for the distances which are much greater than value of r. And ideally, if we are talking about point at infinity, this whole ring behaves as if it is a point charge. So because the formula for the electric field comes out to be kq upon x square. So this is the derivation for the formula for electric field by a ring. Now let us find out the formula for electric field by a half ring. Let's say this is our half ring. We have to calculate the formula for the electric field at the center of this half ring. Not exactly the center, let us calculate it in a general way, but okay, for now. Let us denote this figure. Now, if this has a charge Q, uniformly distributed as usual, this is the part of dq and this is at an angle theta, d theta. What I can say is that the electric field applied by this dq charge would be in this direction, and it would be, this electric field would be, as you know, k dq by, this is r, so this would be r square. So k dq by r square is the formula for the electric field applied by this dq charge in this direction. But we know that, as we can see by symmetry, that if I consider this component of this electric field in this direction, we know that I'll get a counterpart of this similarly here. Because if I consider an element here at an angle theta, I'll get a force, means I'll get an electric field somewhere here, and its component on this side would cancel out this component. So finally by symmetry I can see that the whole electric field would come out in this direction only for this half ring. So if I know that this angle is theta, I can write down that electric field in this direction is k dq sine theta upon r square. And what I'm going to do is, means this is the electric field in this direction by this element, so let's integrate it. Firstly, let's convert this dq. We all know that dq can be written as r d theta. So q upon 2 pi r into r d theta is the formula for dq. That is charge per unit length into the length. So this is q upon 2 pi r into r d theta. So r d theta gets cancelled out. So it would be q upon 2 pi into d theta. So let's write it down here. It would be k sine theta upon r square into q d theta by 2 pi. So if I integrate it from 0 to pi, because this is a half ring, so it can get integrated from 0 to pi only. So we get kq upon 2 pi r square. The integral of sine theta d theta would be minus cos theta. So it would be minus cos theta 0 to pi, and which would give us kq upon 2 pi r square. And if we put the limits on minus cos theta from 0 to 2 pi, 0 to pi, we'll get cos pi is, as you all know, is minus 1. So we'll get, we can take out this minus outside and we'll get minus 1, 2, and this will come out to be 2. So we'll get the formula kq upon pi r square for the electric field by a half ring on its center. So what happens is kq upon r square is put upon like in this direction, and similarly if there was another half ring in the lower part, it would put kq upon r square in the above direction, and thus though if it completes the ring, those two electric field gets cancelled out and you get a zero electric field at the center of a ring. So this was formula for the calculation, or you can say derivation, for the electric field at the center of a half ring. So now let us calculate electric field by a disk on the point that is at a distance x on its axis. Firstly, let us understand something, that in a disk we always provide a surface charge density, which is basically charge per unit area. So surface charge density of the disk which we are considering is sigma, and the disk has a radius capital R. Now, first, before calculating the electric field at any point, let us first calculate the electric field at the point at the center of this disk. I bet half of you will be thinking that the electric field at the center of this disk would be zero. The reason being, if you consider any ring of charges on this disk can be broken into infinite rings of charges. So every such ring will exert a zero electric field on its center. All these rings are concentric. So total electric field by all these rings at the center of this disk would be zero. So maybe some of you will confuse that with the total electric field of the disk at the center. But no, that is not enough. Means that is not the total electric field exerted by this disk on the center of the disk. What happens is, you forgot about the charge which is placed at the center of the disk. Since this is a charge is uniformly distributed over this disk, every point carries some charge. So the center of the disk also carries some charge. Maybe it is tending to zero. So if you take up the formula kq upon r square for this point charge, the q is tending to 0 and the r square is also tending to 0 because we are talking about at the same point. So since there is a uncertainty of 0 by 0, we right now don't know what is the electric field exerted by a disk on its center. Now, okay, just leave that question there only. Firstly, let's find out what is the electric field exerted by the disk at a distance x on its axis. So this is our disk, this will be our axis, this will be center, and here would somewhere be a point x. Now, how are the elements taken on this disk which makes it easy, which makes the question pretty easy? What we do is, we take a ring which is our basic element at a distance r. This ring is taken at a distance r, and the width of this ring is basically dr. Now, the ring as an element is taken at a distance r, and its width is dr. So we know that surface charge density, that is sigma, is the charge per unit area. Now, what is the total charge of this ring on this ring? Total charge on this ring, that is given by dq, can be written as dq is equals to charge per unit area into area. Area would be the circumference into the width of the ring, which would be 2 pi r dr. So this is the value of the charge on the ring. Now, if I consider that ring over here, this ring would exert an electric field of E on the right hand side, that is like this. The value of E, as we all have seen, would be K dq x upon r square plus x square whole to the power 3 by 2. Now if I substitute dq from here, this would be dE, because this is the small electric field put up by a ring at this point. If I integrate this dE for all such rings which vary from r equals to 0 to r equals to capital R, I'll get the total electric field put upon by this disk at that point. So if I integrate this, I'll get E equals to kx integral 0 to r x, and dq can be written as sigma 2 pi r dr upon r square plus x square whole to the power 3 by 2. So this is the formula. Now let us remove this part and let us calculate that formula. It would be E equals to, as you can see, kx sigma 2 pi can be taken out. So kx sigma 2 pi are taken out, and in the integral sign we are left with r dr upon r square plus x square whole to the power 3 by 2. Now what I can do is, I can consider r square plus x square equals to y square. So 2r dr equals to y dy, 2y dy. So r dr is equals to y dy. So I can convert this integral to r0, so we have y equals to x, and when r is capital R, y is root over r square plus x square. R dr is written as y dy upon r square plus x square is y square, so this would be y cube. So this can be taken as x to root over r square plus x square 1 by y square dy. So this integration can be written as minus 1 by y and limits from x to root over r square plus x square. And thus this whole thing can be written as, or the electric field by a disk can be written as k sigma 2 pi x into 1 by x minus 1 by root over r square plus x square. And thus if I consume this x inside, I'll get 1 minus x upon root over r square plus x square. Now always in questions of electrostatics, after getting the final formula, always check out the dimension, that the formula is dimensionally correct, because it may be that you are doing all the calculations in variables, so maybe you did some mistake. If the that mistake would get reflected in the dimensional formula of the final answer that you get. So always in the questions of electrostatics, in variable type questions, when you finally get the answer, you check the dimensional formula of that answer. For here I can check that we know that E is basically kq upon r square. That is, there is a k, okay, k is here. There is a charge which is divided by the length square. So since we have a surface charge density which is charge per unit area, so sigma in itself is q upon r square is the dimension of this. So okay, this is a constant term, this is a constant term, and this is a constant term. So okay, this formula is at least dimensionally correct, so we can hope that we didn't do any mistake in between the calculation. So this is the formula that comes out to be for the formula. Now if I write k by, if I replace k by 1 by 4 pi epsilon naught, I can cancel out this 2 pi with this 2 pi and I'll get sigma by 2 epsilon naught. Now an important point to be noted, that initially I told you that the electric field at the center of the disk is not equals to 0. Now you can see from the final formula which we get that I was correct. Now if I put x equals to 0 in this formula, I'll get 1 minus 0, and thus I'll get E at the center to be sigma upon 2 epsilon naught. So this is the value of the electric field at the center of a disk. Now this is a value of the electric field at the center of the disk, that is sigma upon 2 epsilon naught, and this is the value at a distance x from the disk. Now you can see that if this x is in this case, if x is very small than r, I can ignore r here and it would be 1 minus x upon r, and thus once again I'll get a SHM. But if x was, let's say, much greater than r, I'll get a formula that is sigma upon 2 epsilon naught. It is, you can see that, let me remove this thing, the whole derivation part. Now if in this formula x is much greater than r, I can see that this E would come out to be 0, because if x was much greater than r, I can write this whole thing as x square, and thus 1 upon x, 1 minus 1, and this would come out to be 0. That is, at infinite distance the electric field or at a far distance electric field by this disk is equals to 0. And if x is, let's say, much less than r, the electric field, okay, would come out to be linear, that is sigma by 2 epsilon naught into 1 minus x by r. So this is the formula for the small distances, and that is the formula for the large distance, value for the large distance. Now let us calculate the electric field exerted by a long, infinitely long wire. Infinitely long wire. So, this is a infinitely long wire. You have to calculate the electric field exerted by this infinitely long wire at a distance of x unit. Since it is infinitely long, it doesn't matter that this distance is from what point. So we have to calculate the electric field at this point, which is at a distance of x from this infinitely long wire. What do we do for this is, we take similar element as we did. Firstly, let us note something about the long wire, that it has a lambda charge density, linear charge density. You can say that we studied sigma as the surface charge density. So here linear charge density is defined, which is charge per unit length. Charge per unit length is lambda. So lambda is the charge per unit length for this infinitely long wire. This is a distance x. Let's consider a small element like this. At a distance of y, and this element would be dy. So this element is dy, and this lambda, so at a distance y, it can be taken above or below, it does not matter. So this y, and this is a very small element dy. So let us calculate the charge on this, the charge dq on this small element, charge dq. So dq can be written as charge per unit length into the length, which is dy. So we can easily write down dq to be equals to lambda dy. Now the electric field by this small part of the wire at this point would be something like this, E. Now you can clearly see that similar to this point, at a distance y, I have another point upwards which will exert same electric field in this direction. So electric field, this component in this direction of these two electric field will always get cancelled out, and the final resultant will be in this direction. So I can say that if this is the, let us say this is the electric field by this part, and I consider this as an angle theta. So this is an angle theta. So the x direction component, if I say, would be E cos theta, or I say dE cos theta. So integration of every such component from y belonging to minus infinity to plus infinity will give us the formula for the electric field at this point at a distance x. So let's do it. Firstly, let's write down the value of dE. The value of dE would be k dq upon r square, which would be x square plus y square. So x square plus y square is the distance square. Now this is the value of dE. So let us write down here. It can be written as k, dq can be written as lambda cos theta dy upon y square plus x square. So this is the formula, this quantity. Now what we can do is, we can either substitute the value of cos theta, or we can either substitute the value of y square plus x square. Y square plus x square, which is this distance, the square of this distance can be written as, or let us solve it in y square plus x square only. Now we can write this cos theta as x upon root over y square plus x square. So the formula comes out to be k lambda x dy upon y square plus x square whole to the power 3 by 2. Y square plus x square whole to the power 3 by 2, and we have to integrate it to find the value, and dy is integrated from minus infinity to plus infinity. Now to solve this integration, firstly let's remove the terms k lambda x, and write it down somewhere here. K lambda x is the outside term. We just have to solve this integration to find out the total value of electric field at this point. So we have the integration minus infinity to infinity dy upon y square plus x square whole to the power 3 by 2. Firstly, let us check, are we correct up till now? Since k is okay, we have lambda, that is charge per unit length into length. So we have the unit of charge here. So we must get a unit of 1 by r square from here. Since this is 1 upon, you have a distance unit upwards, you have a distance unit downwards, so you'll get, yeah, if you integrate it, you'll find 1 by y square. Now, let us solve the formula. Let us solve that integration. What we do is we substitute y equals to x tan theta. So if we substitute it, we'll get dy equals to x sec square theta d theta. So we can write this down as minus pi by 2 to pi by 2 cos theta, I can write this down as minus pi by 2 to pi by 2. Dy can be written as x sec square theta d theta divided by y square plus x square. So x square will can come out x cube, and tan square theta plus 1 would be sec square theta. So this can be written as sec cube theta. So if I have a close look, x gets cancelled out with x and 1 x square comes out, and I have to write this x square here, so it can be written as x square here. And what happens is sec square theta gets cancelled out with this, and we are left with only 1 sec theta in the denominator, which can be written as a cos theta in the numerator. So this integration gets simplified to this quantity. So this can be written as, the integration of cos theta can be written as sin theta from minus pi by 2 to pi by 2, and we know that this when we put the limits, it will come out to be 2. So the final formula comes out to be 2k lambda x upon x square. So x gets cancelled out, and thus 2k lambda upon x is the formula for the you can say for the infinitely long wire having a linear charge density lambda at a distance x from any point. But okay, this was infinitely long wire. Let us say under same conditions the wire is in semi-infinite long. That is, it is something like this. It extends to infinity in the upwards direction, and you are calculating at this point. That is at distance x. Now, one way is to again integrate this and find it out. The another way of this can be, we know that if it was a fully infinitely long wire, that is, if it extended in the lower part also like this, the total formula would come out to be, the total electric field will come out to be 2k lambda by x. So this would be the total formula that would come out. So if we just want to calculate the part in the x direction by symmetry, I can say that the electric field put up by the upper part and the lower part are equal in this direction. So if I remove the lower part, I can say that the electric field on the x direction would just be k lambda by x. But is this the total electric field put upon by the semi-infinite long wire on the x? No, it is not, because for this semi-infinite long wire, you will also get a component like this of the electric field. So you have to calculate that component, and the final component, the final electric field may come, means if this is equal, it may come in the middle, or it will come somewhere here like this. So if you want to calculate for this semi-infinite long wire, you can write the expression of this electric field, and you can easily calculate what is the value of this, the electric field in this direction. So this was the calculation for semi-infinite long wire. Now let's study the electric field by an infinitely long sheet. Similarly, as we did for disk, the surface charge density here is again sigma. Surface charge density for infinitely long sheet is sigma. So if I consider my infinitely long sheet as like this, and it extends here, there, here, and there. So it extends in all the four directions, and this is my infinitely long sheet. It is something like this, that is, it is coming out of the plane, but I have drawn its projection like this. So it is something like this. And I have to calculate the electric field at a distance x from this. So let us consider a point at a distance x from it. Now, what is the way of calculating this? We have to choose, as we did for this, an element which would break this infinitely long sheet into equivalent parts so that we can easily calculate that what is the value of the electric field at a distance x. In this case, what we do is we take an infinitely long wire. We know what is the value, or we can say we know what is the value of electric field for an infinitely long wire. So let us consider at a distance y a infinitely long wire like this. So this is the infinitely long wire. So you can see that if this is a sheet, so this is distance y, that is at here somewhere is infinitely long wire, and here is our point x. So what I can see is that if this is the case here like this, and my infinitely long wire is something like this, so the electric field exerted by this infinitely long wire at that point would be in this direction. So I can draw the direction to be something like this, which would be I can say not like this, it would be, if I join this to x, in this direction, because we know that if this is an infinitely long wire, the electric field at a distance, this point would be diagonally outwards, radially outwards. So if this point is at like this, as in case here, so this point is like this, so it would be again be radially outward in this direction, electric field. This electric field can be written as 2k lambda by r, as we derived just now. 2k lambda by r, where r would be root over y square plus x square, wherein lambda was linear charge density of this wire. So if we want to write the linear charge density of this wire, I can write this down as, this is a you can say a length, the width of the wire is dy at a distance y. So I can say, since the surface charge density is sigma, so the sigma is charge per unit area. So if I multiply it by the length, that is dy, what I'll get is the linear charge density of this infinitely long wire, because I cannot write the area of this infinitely long wire. So to get the linear charge density, I'll multiply this surface charge density by the width of this wire, and thus get the charge which is per unit length of this wire. So I can write this lambda, or I can write this d lambda. Which should I write? Because there is a d lambda charge on this infinitely long wire, which can be written as sigma dy. So this is our E, and let's say this was our theta. So as again you can see, similarly this is an infinitely long wire which is making E like this, or I can say DE like this. So if I consider this as an angle theta, I can find a counterpart of this infinitely long wire like here, which would again make a DE in this direction at an angle theta. So again you can see that the y component gets cancelled out, and you will be left with only the x component, which would be, you can see the total, or you can, now you don't need to calculate the x component, you just need to calculate, you don't need to calculate the y component, you just need to calculate the x component, which can be written as dE cos theta, its integral. So dE, which is written as 2k d lambda, which is sigma dy upon root over y square plus x square into cos theta, which can be written as x upon root over y square plus x square. Its integral from y belonging to minus infinity to infinity. Yeah. So this integral can be written as 2k sigma x integral minus infinity to infinity dy upon y square plus x square. So from here we can see that if I substitute y equals to x tan theta, I'll get 2k sigma x integral of minus infinity to infinity means minus pi by 2 to pi by 2, minus pi by 2 to pi by 2, y equals to x tan theta. So x tan theta dy you will get as x sec square theta d theta. So I can write this as x sec square theta d theta whole divided by y square plus x square, that is x square tan square theta, that would be x square sec square theta again. So sec square theta sec square theta gets cancelled out, x get cancelled out with this x. So you are left with this much quantity. So this would become 2k sigma pi by 2 and this would be pi by 2 plus pi by 2, I believe. Yeah, pi by 2 plus pi by 2. So that would be pi. So this is the formula for the, or if I simplify it, it would be 2 sigma pi upon 4 pi epsilon naught. Pi gets cancelled out 2. So you are left with sigma by 2 epsilon naught is the formula for the electric field at a distance x by an infinitely long sheet. Now, an interesting property to be noted is that the electric field that comes out is independent of the value of x. That is, it does not matter whether you are calculating electric field at this much distance or this much distance or much far. So you can see that electric field by an infinitely long sheet is independent of the distance or of the point you are calculating. Now this property is interesting because let us say you have an infinitely long sheet like this. Of positive charge. This sheet is something like this, means it is going in and out. So this is infinitely long here and infinitely long inside. Now you can now you know that this is an infinitely long sheet. Electric field by this infinitely long sheet, as we have calculated, is sigma upon 2 epsilon naught. Now let's say I have a minus q charge, negative in sign only, and magnitude is q. So if I have a negative minus q charge, it will get attracted towards this positive charge. With what force? F, as you all know, is equals to q into E, which would be q sigma by 2 epsilon naught. That means it is getting attracted towards this sheet with a force q sigma by 2 epsilon naught, which is constant. And can you think, why I drew this sheet like this? Do you know? Because in this way you can see that F is, we calculated, it is q sigma by 2 epsilon naught. Now let us say I take a minus q charge material here, and what I do, I throw it with a velocity v in this direction. So what will happen to this? What path will minus q follow? You don't need to calculate the exact trajectory of minus q, but just the idea. What path will minus q follow? The easiest way of solving this is comparing this system with the system of the earth. The earth, as you all know, exerts a constant force of mg on a mass which is, let's say, if I drop this pen like this, the earth constantly puts mg force, that is the force that earth put on this, that is the gravitational force, is independent of the position of this pen. Because the pen was here, then the pen moved in this, moved many points in this trajectory. So at all the points, the force put upon this the pen was mg, that was constant. Similarly, at this charge, the force at every point would be equals to q sigma by 2 epsilon naught, which is equal to the means similar to the force put upon by the gravity. So this the trajectory of this particle would be a parabola, as in the case of motion in 2D, which we study in case of gravitation. Now if you want to write down the formulas for this trajectory, you can easily write down, like we know that if the force was equals to mg, you calculated so many formulas, so you can say F is equals to q sigma by 2 epsilon naught. which can, if it is compared with the mg, means if you maintain the similarity, if it is maintained mg, so you can say g equals to q sigma by 2m epsilon naught. This can be considered as, this is the gravitational acceleration, so you can consider it as a means what you can say, this g is the gravitational pull, so you can say this is the electrostatic pull by this sheet on this charge minus q. So this is an interesting property, that for a infinitely long sheet, the formula for electric field does not depend on the position where you are calculating the charge. Now, interesting question based upon this. Let us say you have 4 infinitely long sheets like this. They are placed like this. It has a charge plus q, or I should say, I am talking about the density. It has a charge minus q, it has a charge plus 2q, and it has a charge minus 3q. Now what you want, or I should say charge intensity, or let me write it down that way only, sigma minus sigma, 2 sigma, 3 sigma. Now let's say you want to calculate electric field at this point, that is at point A, at point B, at point C. What you do is, for calculating the electric field at point A, we calculate electric field by all these 4 sheets by the principle of superposition and add them vectorially. We know that since these sheets are infinitely large, at this point electric field would always be on this direction only, that is in the x-axis only. So these two, the electric field by this plate would be sigma by 2 epsilon naught in this direction, by this plate would be sigma by 2 epsilon naught in this direction, so it will get cancelled out. By this plate it would be 2 sigma by epsilon naught here, and sorry, sigma by 2 epsilon naught is the formula, but okay. So 2 sigma by 2 epsilon naught here, and by this it would be minus 3 by 2. So you can see that it is pretty easy to solve the questions like this, wherein infinitely long sheets are placed and you have to calculate the electric field at any such point. Similarly, you can calculate the value at B. B will have sigma by 2 epsilon naught here, minus sigma, since this is minus sigma, so it would be sigma by 2 epsilon naught here. In magnitude, I am writing the direction, so this would be sigma by 2 epsilon naught. Similarly, for this, it would be 2 sigma by epsilon naught here, and it would be minus 3 sigma by 2 epsilon naught here. So finally, you will get minus 3 sigma by 2 epsilon naught at point B. So these questions are pretty easy, which involves infinitely long sheet, because the electric field of infinitely long sheet is independent of the position you are calculating. Now we move upon to electric field by a hollow sphere. Calculating electric field of a hollow sphere by integration is pretty tough, but I'll give you a hint of it, that how do we do that. What do we do is, let's say this is our hollow sphere. Let me draw it in a bigger so that you will understand it better, because bigger is always better. So this is a hollow sphere. You want to calculate, this is the center of the hollow sphere. You want to calculate the electric field at a distance r from here. How will you do that? By the method of integration. Let's see that first. So what element should we take? Firstly, big question, what element should we take? In a hollow sphere, what right now I cannot think of is, I cannot take a infinitely long wire, I cannot take an infinitely long sheet, I cannot take even a disk, because disk is not the case here, because it is a hollow sphere. The only thing left is a ring. So what I take as an element is, I consider an angle theta and an element d theta. I made this d theta quite big so that you will see it clearly. So this is the element of arc subtended by the angle d theta. So this basically as you can see, and somewhere here also in the background, yeah. So this basically is the ring element which you have to consider to calculate the value of the electric field at a distance r. So this is a ring element theta. This is a ring element of, you can say this, if this is capital R, so this length is r d theta. So this is r d theta. So this ring you have to consider, and if you want to calculate the radius of this ring, the radius, okay, this, let's take this distance as x. The radius small r of this ring would be r sine theta. So you get the radius of this ring as r sine theta. You know the hollow sphere will have a surface charge density as sigma. So you can find out that dq charge on this ring can be written as, since sigma is the surface charge density, sigma upon total area, that is 4 pi r square, into the area covered by this ring, which you can clearly see would be 2 pi r sine theta into r d theta. So it would be 2 pi r sine theta into r d theta, and this r is capital R square. So this would cancel out to 2. So this would be sigma sine theta d theta by 2 is the dq charge on the ring. Now this is the value of the charge. Now in similar way, what you can do is you can calculate the electric field of this ring here, and you can write it as kqx upon r square plus x square whole to the power 3 by 2. Then if you will proceed the calculation and substitute the value of dq, you will find that integration becomes quite big, and means it takes a much longer time to solve the integration for this. So I'll give you a better method of solving this part, that is of finding the electric field exerted by the hollow sphere at a distance x outside by a Gauss theorem, which we'll be learning shortly. So after we learn Gauss theorem, we'll calculate the electric field exerted by hollow sphere in just 2 minutes, I can say that. So let's, for the sake of studying, let's for now study the direct formula of the electric field exerted by a hollow sphere. For a hollow sphere, you have actually two cases. Let's say its distance is r and you are calculating electric field at a distance x. So the electric field at a distance x is given by kq, where q is the total charge on this, kq upon x square if x is greater than r, and if greater than equals to r, and if x is less than r, then this electric field is equals to 0. So this is the formula for the electric field exerted by a hollow sphere at a distance x. That is, if the point at which you are calculating the electric field lies outside the hollow sphere behaves as a point charge, and thus the electric field comes out to be kq upon x square, that is x is the distance from the center. Whereas if the point at which you are calculating the electric field lies inside the hollow sphere, the formula, the electric field exerted by that hollow sphere is 0. So this is something about electric field exerted by a hollow sphere. Now let us study electric field exerted by a solid sphere. Electric field exerted by a solid sphere. In case of solid sphere, we'll basically use the result derived in hollow sphere. Let's say this is a solid sphere having a total charge q. So firstly, talking about any exterior point, that is any exterior point at a distance x. For calculating electric field at a distance x, what I'll do is I'll consider various hollow spheres inside this solid sphere. So if I consider any hollow sphere inside this solid sphere, I'll get that the formula would be k dq upon x square for every hollow sphere which lies inside the solid sphere. So if I want to integrate this k dq upon x square, k upon x square would come out because they are independent of dq, and integration dq can be written as kq upon x square, because the total the sum of all the charges of these rings has to be equals to the total charge q. So for any point which lies outside the solid sphere, the electric field is kq upon x square. That is, this solid sphere also behaves as a point charge for any point that lie outside its boundaries. So if x is greater than or equals to r, kq upon x square is the electric field. Now, what happens if this x lies inside? So this is a solid sphere, and if this x lies inside, you have to calculate at this distance x. What will you do? The best way of doing this is, let us consider once again hollow sphere. So if I consider any hollow sphere which is outside this distance x, that is, let's say I consider hollow sphere which is in blue color. For that hollow sphere, what I can say is that for that hollow sphere, the point at which we are calculating electric field lies inside that hollow sphere, and we know that for any the electric field inside a hollow sphere is 0, as we studied just now. So we can say that electric field exerted by this blue hollow sphere at a point which is inside this hollow sphere is 0. So at this point it would be 0. Now, if electric field by this hollow sphere in blue is 0, we can assume that there is the boundaries outside this hollow sphere made at a distance x does not put any effect on this. So the only thing which is left is the inside part, and we know that we can treat this inside part again to be another solid sphere, and for that solid sphere the point, this x point, lies at the radius, and we know that the formula is kq upon x square, where this q would be, this small q would be the charge of this small part of the solid sphere. So this small part q, since the q charge is uniformly distributed, we can write this q charge as q upon 4 pi r cube into 4 pi x cube. So this becomes qx cube upon r cube. So the charge here is qx cube upon r cube. So if I substitute this charge, it would be kqx cube upon r cube. So finally the formula comes out to be kqx upon r cube if x is less than r. So you can see that for a solid sphere, kq upon x square is the formula for if x is greater than or equals to r, and kqx upon r cube if x is less than r. So if I draw the graph of this electric field with respect to the distance x till the distance r, this would come out to be a straight line, and after that it would come out to be like this. It would come like this. Yeah. So this is the graph of the electric field based upon how the x, that is the distance from the center, varies. So this is the value of electric field when the point is inside the solid sphere, and this is the value of electric field when the point is outside the solid sphere. So here we come to an end to the topic electric field. Now let us study something about electric line of forces. Electric lines of forces, actually. What do we actually mean by electric lines of forces? Electric lines of forces are basically imaginary lines which are drawn for our own convenience, which shows that means at any point on this line, if you draw a tangent, it will show that this is a directed line. So at any point on this imaginary line, if you draw a tangent, that tangent would give the direction of the electric field at that point. So these lines, such lines are known as electric lines of forces. And why are they known as electric lines of forces? Because at that point, since the direction of electric field is along the tangent, the direction of force at that point, at a charge placed at that point, would also lie along the direction of the tangent. So that's why they are known as electric lines of forces. Let's study some of the properties of electric lines of forces. Firstly, the basic one. Let's say if you have a plus Q charge. You know that electric field, as we all know, is defined as force exerted on a unit positive charge. So all unit positive charge will be repelled by this positive charge. So if I talk about electric field at this point, we know that it is radially outward. So it would be like this. So if I want to draw electric lines of forces, I can draw a line like this, because on this line at every point electric field lies along this line. Similarly, I can draw a line like this. Similarly, I can draw a line like this. Similarly, electric lines of forces of a positive charge, independent positive charge, can be drawn like this, all radially outward and extending till infinity. Now, this was an independent case. Let me draw a boundary here. Now, if I consider a negative charge, we know that it will attract the positive charge which we are talking about. So the electric lines of forces are like this, entering in the negative charge, because at any point on these lines you can see that electric field would be directed towards the negative charge. And this again I am talking when this negative charge is independently placed in the universe. Now, this independent system of positive charge has electric lines of forces like this. This independent system of negative charge has electric lines of forces like this. What happens when I remove this boundary? What happens is, so let me draw it a better way. Okay, boundary is still there. So here is the boundary and here is our negative charge. So we have something like this, we have something like this, and similarly from every direction we have lines like this. Now, what happens when I remove this boundary? When I remove this boundary, what happens is that this joins, and this, instead of going to infinity, curves here like this. This again, instead of going to infinity, curves like this, and this line also bends like this. This line also gets bends like this. This also gets bent. This one also gets bent. But here the line remains like this, and similarly here this line gets bent like this. This line gets bent like this. This line gets bent like this. This gets bent like this. So these are the electric lines of forces when a positive and a negative charges are kept together. As you can see, if I place any plus or any, let's say if I talk about this point, if I place a unit positive charge here, it will start moving in this direction until it reaches minus Q. So you can see that electric lines of forces originate from the positive charge and terminate at the negative charge. So this is one of the properties of the electric lines of forces, as we know. Another property of electric lines of forces is that electric lines of force, that is, two electric lines of forces never intersect. The reason being, let us assume that they intersected at a point like this. So at this point, I'll have an electric field, means one line of force will give that electric field's direction is here, and the another will give that electric field's direction is here, which is not possible because total electric field at a point can have only one direction. So this proves that electric lines of forces cannot intersect with each other. Now, another property of electric lines of forces says that the more the density of electric lines of forces, the more is the value of electric field there. That is, let's say, not like this, let's say electric lines of forces were something like this. Now, if I consider a point here, point A, and if I consider a point here, point B, we can say that electric field at point A is greater than electric field at point B, because the density of electric lines of forces is greater at point A than at point B. So the property says that the more the dense the electric lines of forces are, the more is the value of electric field. So this was a property. Another property is that number of lines that originate from a charge is directly proportional to the amount of charge or to the value of the charge. That is, if let's say I place a 5 coulomb charge and 10 lines get 10 electric lines of forces originates from this charge, then from plus 10 coulomb charge 20 lines of forces will be originated. So this is another property of electric lines of forces, that the amount of electric lines of forces is directly proportional to the magnitude of the charge. Now this was something about electric lines of forces. Now let's move to the electric flux. After talking about electric lines of forces, let us say that these were, let's say, electric lines of forces. So if I consider let's say let me draw it in another color. Right. Let us say that these are this is one electric line of force. Let us consider only one electric line of force. Now, if I draw a area segment, small area segment of ds area with this is an electric line of force, and if I draw a ds segment, that is a segment of area through which this electric line of force passes, that is electric line of force across this ds segment of area, and this is the direction of the ds. We all know that direction of a segment of area is perpendicular to the surface. That is, since this is the surface, this is the direction of the ds, and this is the direction of the E vector at the point where this electric line of force intersect with the surface. So this is the direction of E. Now, electric flux through this surface. Electric flux is means you can say a hypothetical quantity defined. Electric flux is defined as firstly denoted by phi. D phi is equals to E dot ds. So this is the formula for the electric flux through this surface. Electric flux is a hypothetical quantity defined, that amount which is passing through this surface d phi is equals to E dot ds. So this is the mathematical formula for electric flux, and understanding flux in a physical way is a much difficult topic in itself, that how do we look upon what is flux through a surface. Okay, means there is no way of looking it in a physical way. So let's understand it mathematically only. So d phi is equals to E dot ds is the formula for the electric flux. Now, if this is the formula, now let's take some cases. Let's say this is a let us say that these are the electric lines of forces, like this, parallel to this plane of the board. Now, if I choose a rectangle which is something like this, or square which lies in the plane of the board itself, so ds vector would be something like this coming out of the plane, and E vector is here. So you can clearly see that the angle between the ds vector and the E vector is equals to 90 degree. So E dot ds would be 0. So you can say flux total through this surface area is equals to 0. So surface area means if electric field is parallel to the surface area considered, then the flux through that surface area would be 0. Now, instead of considering it like this, I consider it, let's say, like this. Like this. So I can say that E and ds are in the same direction. So E dot ds means E ds cos theta. So cos theta would be 1, And if this area is A, or let's say if this is a square of side R, so I can write this down as phi total is equals to E into R square. So this is the formula for the flux through this square plate, which a square area which I have considered like this. So these are the means in this way you calculate the value of the flux. Now let us try and do same thing for the hemisphere. Or maybe probably firstly we should do it for a ring. Let us say this is a ring and we have electric lines of forces like this. So you can clearly see again the angle between E and ds is 0. So the flux total will come out to be E into pi r square. So this is the flux total through a ring. Now let us calculate total flux through a hemisphere. Again, electric lines of forces are like this. So if I calculate it at any point here, ds would be something like this, radially outward, and E is something like this. So I can say that at that point E dot ds, I can write it down as this as theta. I can write this down as E magnitude into ds magnitude cos theta. Now the point to be noted is, what is ds cos theta? What is basically, firstly let us understand what is ds. ds is a small element on a hemisphere which is something like this, maybe something like this, a pretty small element, something like this. So and its angle is like this because its normal is like this. And what is ds cos theta as a whole? ds cos theta is the projection of this area. You can say, okay, let me magnify this area. This ds is something like this, a small piece, and the normal is here, and this is the theta. So what is ds cos theta? ds cos theta, this is an area. So what is ds cos theta? ds cos theta is, this area is something like this on the hemisphere. If this is the whole hemisphere, this area would be something small here. Means this is the hemisphere, this area would be something like this. If I magnify it, it would be something like this. If this is the area, this is ds, and what would ds cos theta be? ds cos theta would be the projection of this area in this direction. That is the projection of this small part of area on the base of the hemisphere. So ds cos theta being considered as the projection of this area on the base can be written as E dot pi r square. So E dot pi r square is the, again this is valid for the ring and the hemisphere. Now I can probably tell you that how to understand electric flux physically. As I took hemisphere, let us once again take hemisphere, and electric lines of forces are like this. Now let's say instead of taking a hemisphere, I would have taken a figure like this. We know that projection of every means we considered here just a hemisphere, but here also projection, small projection of the areas will be equal, not outside, this is inside. So small projection everywhere would lie on the whole ring. So for this also flux would be E into pi r square, E into pi r square. For this also flux was E into pi r square. For let's say any random figure like this, I mean this can't be a solid figure, it is flux is E into pi r square. So now you can get that flux can be seen as the number or the amount of electric lines of forces that pass through that area. Since these electric lines of forces are equal in all the three cases, we get equal amount of flux. So you can think of flux as the number or the amount of electric lines of forces that pass through the area being considered. So this was basically concept of electric flux. Now let's move on to Gauss law. Gauss law is a very strong technique, and as I told you that in this topic I'll be deriving the formula for the electric field by a hollow sphere in just 2 minutes. So let's study basically what is Gauss law. The statement of Gauss law says that You consider a closed surface. You consider a closed surface means in 3D, if you consider a closed surface, the flux through that surface, total flux which pass through that surface is equals to Q in upon epsilon naught, where Q in is defined as the total charge that lies inside that closed surface. So basically, you choose a closed surface in 3D space. You find what is the total amount of charge inside that closed surface or on the closed surface. So flux through that closed surface by everything means it's not flux due to the inside charges. Flux due to anything in the universe through that closed surface would be equals to Q in, that is the some total charge that lies inside that closed sphere, divided by epsilon naught. Excuse me. So this is basically the statement of Gauss law. Now let's apply this statement of Gauss law and verify this Gauss law, you can say, or verify the formula which we got before for electric field. Let's first talk about the hollow shell. As I told you, I'll be deriving it, hollow sphere. And you'll find out derivations through Gauss law of electric field are pretty easy, but they require a symmetry. So we'll see to that. Now let's say I talk about this hollow sphere. If I want to I know that total charge on this is Q, which is uniformly distributed. Now if I want to calculate electric field at a distance r, by symmetry I can say that if I draw what you can say a hypothetical circle of a hypothetical sphere of radius r with center being the same as the hollow sphere, at every point on this sphere, the hypothetical dotted blue line, so at that sphere I can say that at every point electric field is same and is, let us assume it is means by symmetry I can say that it lies radially outwards. So here is E, here is E, here is E. So at every point outside E is like this. Now if I consider my closed surface to be this whole thing, means the sphere, the hypothetical sphere of dotted blue line as my Gaussian surface, as is called, means the surface which I choose to apply the Gauss law is known as the Gaussian surface. So if I choose this as my Gaussian surface, I can write the formula that phi total I can write down, because every time E and any small element, if I consider of the area, E and ds, every time E and ds lie in the same line, that is E dot ds is equals to E into ds, because cos theta is 1. So E dot ds phi total can be written as E into 4 pi, sorry, this distance must be x because I am calculating at a distance x. So 4 pi x square. This is the phi total at the Gaussian surface, because in the universe only a hollow sphere is there. This is equals to Q in. Q in is total charge inside this hollow sphere, inside the hypothetical Gaussian surface, that is equals to Q upon epsilon naught. So E would come out to be Q upon 4 pi epsilon naught x square, which is equals to KQ upon x square. So hence we derived the formula which I told you, that for any point outside the sphere, a hollow sphere behaves as a point charge. So we got the electric field to be KQ upon x square. So now you can see the strength of the Gaussian law, Gauss law. So this is one of the derivations. Now if I consider, similarly if I consider a point inside at a distance x, I can write down E into 4 pi x square equals to 0 upon epsilon naught, because the charge inside this Gaussian surface is 0. So you will get E equals to 0 as I told you in the formula for hollow sphere. Now, if I want to derive similar formula for solid sphere, I can do similar thing. I can, for any point outside, I can write E into 4 pi x square equals to Q upon epsilon naught, which would be equals to KQ by x square as was derived for solid sphere, and for out, this is for the out, and for inside, I can write E into 4 pi x square equals to Q inside, which can be written as Q by 4 pi r cube into 4 pi x cube divided by epsilon naught. So 4 pi gets cancelled out. This 4 pi will go with this epsilon naught and form k, and this x square gets cancelled out, and you are left with kqx upon r cube, which was the formula derived for the solid sphere. Now, let us take more example so that you will be able to know that how Gaussian surface are taken. Let us calculate electric field for a infinitely long sheet. So let us say that this is our infinitely long sheet. So how do we consider a Gaussian surface so that this law provides us the electric field at any point? The choice of Gaussian surface is really difficult and is, I think, question specific. So every time you face a new question, you have to think on yourself and you have to get a new Gaussian surface. Like for example, for an infinitely long sheet, what a Gaussian surface is a cylinder. Let's say if you want to calculate at a distance x, what you choose is a cylindrical Gaussian surface, something like this. If you want to choose at a distance x, so this is a solid sheet, so you make a cylinder on both sides at a distance x. So if I take electric field, I can assume it is E, which is equal, and here also it is E, which is equal E. And now if I want to write down the formula, I can write down that E for, let's say, I can take this as sum of three surfaces, surface 1, surface 2, and you can say the circular part, that is the lateral area of the cylinder. So for surface 1, I can write down flux as E into pi x square. For surface 2, I can write down flux as E into pi x square. And for surface 3, that is the lateral surface, I can say that electric flux is here in the direction, and for lateral surface ds is here. So this would be E1, but the direction of E1 and ds means they both are perpendicular to each other. So flux through the lateral surface is actually 0. So this plus 0 is equal to charge that lie inside this Gaussian surface. Charge that lie inside this Gaussian surface, we know that surface charge density of this infinitely long sheet is sigma. So this can be written as sigma into pi x square, because the charge which would lie inside would be a circular region. So it would be pi x square upon epsilon naught. So pi x square get cancelled out, and E comes out to be sigma by 2 epsilon naught. So you can see that deriving any formula with using a Gaussian law for any electric field is pretty easy. Now we may also derive one more formula for an infinitely long wire. Let us say this is an infinitely long wire. Now, how to choose a Gaussian surface for this infinitely long wire? We want to choose a surface like this so that there is a symmetry, so that we can write the value of electric field in a single form so that we can derive it properly. So if you want to find out electric field at a distance x, what you can do is, by symmetry you can say that if I take a circle around this, I'll get the same value of electric field at every point. By symmetry I can say around at every point on this circle, electric field would be equal and direction would be something like this. But I can't take this as a surface because this is not a closed surface in 3D. So let us extend it. Let us consider a cylinder like this, and at every point here E is there. Here also something is value is there. Now let us say that the length of this cylinder taken is L. Now I can write down flux as as a sum of three surfaces. This is surface 1, this is surface 2, and the lateral surface. Surface 1 you can see by, we know that this the electric field on this surface would be in this direction, and for surface 1 the ds would be like this. So for first surface, the electric field and ds are perpendicular to each other, and thus they have an angle, that they have 90-degree angle, so the value of the flux on the first surface is 0. Similarly, on the second surface, the value of the flux is 0. If we talk about the lateral surface, we can write down E into 2 pi xl, where L is the length of the cylinder, is equals to Q in, which is just this part of, means this part of the wire which lies inside. So we can write down this formula as, we know lambda is the linear charge density, so we can write this down as lambda into L upon epsilon naught. So LL gets cancelled out and E comes out to be lambda upon 2 pi epsilon naught into x, which can be written as 4 pi epsilon naught into 2. So this comes out to be 2k lambda by x, and this is the formula which we derived for the electric field at a distance x from an infinitely long wire. So these were some basic things about Gauss law, in which we found out that if we choose a proper Gaussian surface, then solving the questions of electric field becomes quite easy. So here we come to an end to the topic electric charges and field. In this topic we started studying that what is basically electrostatics, what are electric charges, then we studied what are electric fields, what are the electric fields for various various shapes. We studied for ring, we studied for half ring, we studied it for disc, infinite long wire, infinite long sheet, and there we completed the electric field. Then we studied electric lines of forces, then we studied flux, then we studied Gaussian surface, and then at the end we studied Gauss law. I know that this topic was quite big, and seriously this topic is quite difficult, so but I hope that you got the topic easily. But if not, you can go back and look at the point wherein you have a problem and try and solve this problem as quickly as possible, because this would be the base of the future electrostatics that you will study. So I hope you enjoyed the lecture. Thank you very much.